Hi, pre-calculus students. How you doing today? Welcome to chapter 3.1, chapter 3, section 3.1. Very small chapter, but really great to refresh before an ACT or before you go off to college or before calculus. So these are exponential functions. Number one, the definition of an exponential function, you study this in Algebra 2, is if you have an initial amount, we call A, or we can call it anything. It just is in that position. We could call it a P. Sometimes we call it a C. Anyway, times some base, right? And the base tells you what you're multiplying by, your initial amount by, over and over, this many times, you're multiplying that base, right? If this was 3 to the 4th, right? That's 3 times 3 times 3 times 3. Right, that's 81. So this tells you, first of all, the base is that you're multiplying 3. The exponent tells you how many times. So when you have an initial amount and you keep multiplying over time, you get an output amount. There we go. And so that's an exponential function. It's kind of the way the real world grows and decays. Your base is never 1, because otherwise you won't see growth or decay when you keep multiplying by 1. If your base is greater than 1, then you're going to see growth from your initial amount. If your base is less than 1, like a 1/2, you're going to see decay from your original amount, right? So common bases are 2, because we like to double things. So if you keep multiplying by 2, of course, you're going to grow from your initial amount. Half-life is how things decay in our world. So if you keep multiplying by 1/2 your initial amount, your amount's going to decay. Wanted to know, what point do 2 to the x, 5 to the x, and y equals 10 to the x all go through? We usually do this in class, but we are not in class. And so if you put each one of these on your calculator on a y1, y2, and y3, you would see that they all go through the point, you may already know the answer, 0, 1. Why is this true? Because anything to the 0 power is 1. So 2 to the 0 is 1, 5 to the 0 is 1, 10 to the 0 is 1. They all go through the point 0, 1. Now, what is the approximate value of E, right? You learned about the base of E in Algebra 2. And E, if you hit, there's 2 places on your calculator, above on the left, above the natural log button, or on the right, above the division button. So if you hit second division and you get your E and you hit enter, you get 2.71828 repeating. So what is E? Where does that come from? And the 1828 keep repeating. Here's where it comes from. E is supposed to be a base that shows natural growth or decay. Well, how is 2.71828 repeating natural? Here's why. Because let's say that you start out with one thing, and it could be you, like when you're a baby. Here's you, 1, right? Now, and just think of you growing over time in seconds, right? So like a huge number of seconds, right? Instead of years and things. So just imagine, because that's how you grow. You grow little bits over long, long periods of time, right? So let's say here's you, right? Plus you're young, you're growing, right? And these are the seconds, x equals the seconds. Well, notice if your seconds are huge, in the millions, then 1 divided by those millions is a very, very small number, right? 1 divided by 10 million, it's very, very small. So if this were you, plus you have a little bit of growth over long periods of time, as that x approaches infinity, what you find is if you put this in the calculator and make x get very big, it approaches E, because that's what natural growth is, right? Little bits of growth over long periods of time. Okay, so this means that natural growth is still an exponential function. Here's your starting amount. Here's your time. So a lot of times they use t for time instead of an x. So you'll see a t here or here, like you do here, right? But the base is e to the r. right? So the entire base is an exponential expression. It's e because it's natural, and the r is positive because it's growth. That's your base. Right here for natural decay, you would see again, here's your initial amount, here's time going by. This is now your base because it's natural, it's an E, and because it's decaying, you'll see that your R is negative. We also, in our real world, do what's called continuous compounding, which means we make our growth of money, very small amounts of growth over long periods of time. So we get to use a base of E in this formula. You probably remember using this. So principal is the amount you deposit or borrow. Base of E means continuous compounding, like natural growth. R is your rate that you are paying or being paid in interest as a decimal. And T is the time going by. So when you deposit so much money and it continuously compounds at a certain rate over time, you get an output amount. So again, it doesn't matter what we call these letters here. It's your initial amount, A, P, whatever you want to call it, okay? Here's your base. And again, here for the X's or the T, it does not matter what you call it. It's in this position and it's time going by. So let's try some examples. It's actually kind of nice and easy, right? So I just wanted to make sure that you know how to use your calculator. Number 34, if you have been given e to the x and they want you to evaluate it where x is 3.2, literally I'm just asking you in the calculator to put in e to the 3.2 and round it to the third place, right? So that would be above the ln button. So left above ln or above the division button. Okay, so I'm going to go ahead. I'm going to use the e to the x above the natural log button, and I'm just going to put in a 3.2 for the x, and that is, need a little room, 24.533. On numbers 52 and 56, they ask you to solve these exponential equations using a one-to-one property. That means to get the bases the same. Okay. Later on in section 2.3 or 2.4, we will use calculators to solve problems like this because you can't always use the one-to-one property, but solving exponential equations using the natural log always works. Okay, so we're just using the one-to-one property here and here because we can. Later, we'll be presented with problems where we can't, and I'll show you what I mean. How do we use the one-to-one property here? I see a base of 2 on the left and a base of 16 on the right. So what if I made them both with a base of 2? I could probably solve for this x easier, okay? So let me give myself some room here. So 2 to the x minus 3 equals, now I'm going to write 16 with a base of 2. So 2 to the 4th is still 16, right? Now, notice that it says that this expression on the left and the right are equal. The bases are equal, so the only way this can be true is don't these exponents have to be equal to each other for this statement to be true, right? And so now I can just say, well, I just need the exponents, x minus 3 to equal 4. I just need this to be true. And when we add a 3 to both sides, we get x equals 7. Okay, if I put a 7 here, 2 to the 7 minus 3 is 2 to the 4th is 16. It worked. What do I mean by when can I not use the one-to-one property? Here's what I mean. What if I had 2 to the x minus 3 equals 17? I can't write 17 with a base of 2. Can't use the one-to-one property. So let's look at number 56 then. They want us to use the one-to-one property. I'm just going to work above here. Notice that it says the left-hand expression equals the right and the bases are equal. The only way that can be true, right, is if the exponents are equal. right? And so I just need 2x minus 1 to equal 4. So I'll add a 1 to both sides and divide by 2. Here we go. Let's try one more problem. Let's use A equals P e to the RT. So let's say $5,000 is deposited into a trust fund that pays 7.5%. And it's going to sit there for 50 years. And the money is going to go to a college. And there's continuous compounding, which means we get to use this formula here with the E in it. And they want to know how much, what will be the output amount after those 50 years. So let's fill it in. We're looking for the output amount. Our principal, our initial amount was 5,000. E, our rate as a decimal is 0.075, right? And the time was 50. So I'm literally just going to run it through the calculator like you see. In this case, we'll round to the second place because it's money, right? So let's see, 5,000 times E. And my exponent is 0.075 times 50. Don't even need to do that first. I just popped it in, right? That grows to, can you believe it? $212,605.41. Isn't that crazy? At 7.5%, how fast that, how big that that amount of money becomes. And just making sure that I put it in right, because even me, that's like amazing. Yep, we got it right. So hope you enjoy section 3.1. Have a great day.